Hello everyone, this is Sir Aris. Today, let us talk about linear dependence and independence. We say that three vectors A, B, and C are linearly dependent when a linear combination of them, let's say vector A times a number A, B times B, C times C equals 0. Where A, B, and C are all non-zero numbers. The unit vectors, for example, I and j, or the unit vectors I and j, for example, they are linearly independent because there are no numbers a and b which are not both 0, such that linear combination ai plus bj is 0. Again, I here is the unit vector along the x direction. J is the unit vector along the y direction. Independent vectors are referred to as basis vectors since all the other vectors can be written in terms of them. So for example, I and j being linearly independent, any vector on the xy plane can be written as a linear combination of I and j. So any vector can be written as a sum of I and j with a and b being specific for that vector. We say that functions f1, f2, f up to fn are linearly dependent if some linear combination of them is identically 0. We use the same similar definition as for vectors to those of functions. So if there are constants k1, k2 up to kn, such that k1 times f1 plus k2 times f2 plus up to kn times fn, if this is 0, then the functions are linearly dependent. So let's consider, for example, sine squared x and 1 minus cosine squared x. Let us show that they are linearly dependent. If we add sine squared x by 1 minus cosine squared x, it doesn't tell us that the total is not 0. So it doesn't actually tell us anything about their linear dependence or independence. So we need to find the specific combination such that when we add them, the answer is 0. So one example, the one that gives us this equal to 0 would be if this is negative or this is minus, so that you have sine squared x minus 1 plus cosine squared x. Sine squared x plus cosine squared x, that's 1 minus 1, and this is 0. Okay. Another example, sine x and cosine x are linearly independent since there are no numbers k1 and k2 not both 0. So whatever k1 and k2 which are non-zero, we can never find something that gives a combination of sine x and cosine x equal to 0. So sine x and cosine x are linearly independent. To determine that a given function or given set of functions is linearly independent, we can use the following theorem. If f1, f2, fn have derivatives of order n minus 1, and the familiar determinant w is not equal to 0, then the functions are linearly independent. This determinant w we already encountered previously. This is called the Wronskian. If you can recall differential equations, so when you techniques in solving second order differential equations, you may have encountered the Wronskian. For example, show that the functions 1x sine x are linearly independent. So we simply determine the Wronskian if it's 0 or not. So for our w, we have 1x sine x. Take the first derivative, that's 0, 1, cosine x. Take the second derivative. There are three functions, so you need up to second derivative. 0, 0, negative sine of x. And then you take the determinant. So determinant, you can use this matrix element times positive 1. So that's 1 times its minor. So 1 minus sine x, negative sine x times cosine x times 0. So this is negative sine of x. This is only 0 for some values of x, but for all other values of x, this is not 0. So they are linearly independent, just like what we have mentioned here. For linear, functions are linearly dependent. Actually, this should be w equal to 0. So this is supposed to be w equals 0. And here, when functions are dependent, we will always get w equal to 0. But in times when we get w equal to 0, it doesn't automatically mean that our functions are dependent. Okay. Sometimes you may be asked to show when that functions are dependent. So you can make use of this Wronskian. But in times when you find solve for the Wronskian without knowing initially, or without being asked whether what are the nature of the functions, whether they are linearly or independent or dependent, one cannot give a conclusion for whether which would be the case. Okay, so there would be, so this doesn't follow conversely. When functions are dependent, it means that w equals 0. But when w is 0, it does not always mean that the functions are dependent. Now let us consider the special case of a set of linear equations when the constant coefficients, what I mean by this are those functions or the terms on the right hand side, the coefficients of the constant term, they are all 0. These are called homogeneous equations. Homogeneous equations generally are never consistent. They always never inconsistent. They always have the solution all unknowns equals 0. In this case, it's called the trivial solution. If the number of independent equations, that is the rank of the matrix, is the same as the number of unknowns, then the only solution is this trivial solution, 0. All unknowns equals 0. If the rank of the matrix is less than the number of unknowns, there would be infinitely many solutions. So if you can recall, the rank of a matrix is the number of non-zero rows remaining when a matrix has been row reduced. So it also tells you the number of independent equations. So for example, let's consider a set of equations here. This is the constant, the coefficients of the constant term on the right hand side. This would be the left hand side would show us the form of the equations. So you have x plus y, x minus y. You row reduce this one, it would give you 1 0 0 0 1 0, which would have a rank 2. So this is rank 2. The only solution is x equals y equals 0. So you can never have any other solution. Consider the set of equations x plus y equals 0 to x plus 2y equals 0. In this case, the row reduced matrix is 1 1 0 0 0 0. One row has 0 terms, So the rank is 1. This is less than the number of unknowns. So there would be infinite number of solutions. The solution are all points on the line x plus y equals 0. For a set of n homogeneous equations and n unknowns, these equations have only one trivial solution unless the rank of the matrix is less than n. Now, when the rank of the matrix is less than n, it means that one of the rows is 0, or at least one of the rows is 0. Then, if you want to solve for the determinant is 0. Okay. In general, a system of n homogeneous equations in n unknowns has solutions other than the trivial solution if and only if the determinant of the coefficients is 0. So this is one way to determine if there are trivial solutions. We set the determinant to 0. For example, for the values of lambda, does the following set of equations, these equations have non-trivial solutions for x and y. Okay, so if you want this to have non-trivial solutions, then the matrix of the coefficients should be in this case should be 0. Okay, so that we'll have non-trivial solutions. And then also another task here is that for each value of lambda, find the corresponding relation between x and y. This is an example of an eigenvalue problem. The values lambda are called eigenvalues, and the corresponding vectors x, y are called eigenvectors. So here we will find relations between x, y for one corresponding value of lambda. Okay, so first step, we set the matrix of coefficients. So the matrix of coefficients, I mean, we write the coefficients of x in one column, coefficients of y in another column. We set actually the determinant of the matrix of coefficients to 0. So you have 1 minus lambda, 2 here, and 4 minus lambda. Okay, so for this, you have 1 minus lambda times 4 minus lambda minus 2 times 2, which is 4. Okay, 1 times 4 is 4, minus lambda is minus 4 lambda, minus lambda plus lambda squared minus 4. 4 cancels. So you have negative 5 lambda plus lambda squared equals lambda minus 5. So the solutions are lambda equals 0 and 5. Okay, for lambda equals 0, we can set, say, the first equation. This lambda to 0, you have x plus 2y equals 0. So the vectors would be such that if there's one value of x, then there's a value of y which satisfies this equation. Okay, if you use this second equation here, set lambda to 0, you have 2x plus 4y equals 0. Well, divide by equations by 2, you get x plus 2y equals 0. For lambda equals 5, okay, you set this lambda to 5, you have 1 minus 5. Oops. 1 minus 5x plus 2y equals 0. So you have negative 4x plus 2y equals 0. Divide what's this by 2. You have 2x minus y equals 0. If you use the second equation, set this to 5, you have 2x minus y equals 0. You get the same equation. So we have for the two eigenvalues, lambda equals 0, lambda equals 5, we have corresponding relations between x and y, x plus 2y equals 0 and 2x minus y equals 0 respectively.